In this video, we will talk a little bit about valence electrons of the main group elements and a few transition elements. And then we will take a look at what the number of valence electrons and whether or not it's a metal or non-metal have to do with the ionic charge. So I have a periodic table here on the screen that breaks down the main group element transitions. I've left off the lanthanides and actinides, which are the two rows at the bottom of the periodic table. And what we're going to do first is just start by taking a look at how do the number of valence electrons change as we go through the periodic table. So what I have here on this slide are the valence electron Bohr models. So remember, the Bohr models show us everything, the nucleus, all the electrons. We're going to use the Bohr models to once again find those patterns with respect to valence electrons down groups. So here, just to point out, we only have the main group elements. So we have group 1, group 2, and then in between these two groups would be all those transition metals, group 3, group 4, group 5, group 6, group 7, and group 8. So we can see all of the main group elements for the first 20 elements. And what we want to do is we just want to find those patterns again with respect to valence electrons. Remember, valence electrons are the outermost electron. So if we look down group 1, for whatever reason, they included this second orbital for hydrogen, but notice there's no electrons here. And if there's no electrons, then that orbital can't exist. So if we look at that n equals 1 electron, which is the only orbital, n equals 1 orbital, excuse me, which is the only orbital that hydrogen has, we see that there's 1 electron. That 1 electron is the only electron that hydrogen has, and it's the valence electron. If we drop down a period to lithium, still in group 1, we see its outermost shell is populated with 1 electron as well. So lithium also has 1 valence electron. Sodium has 1 valence electron and is also at the n equals 3 orbital. And potassium has the n equals 1, 2, 3, 4 orbital, and it has 1 valence electron as well. So the pattern down group 1 is that it has 1 valence electron. If we look at group 2, we see that beryllium has an n equals 1 and n equals 2 orbital. And in its outermost orbital, beryllium has 1, 2 electrons. If we go down a period, we see that magnesium has added an orbital. So its valence orbital is n equals 3, but magnesium also has 1, 2 valence electrons. And calcium adds yet another orbital, but still only has 1, 2 valence electrons. So the pattern as we go down group 2 is that each of these elements have 2 valence electrons. Now, remember, we're going to skip transition metals, which would be between these two groups. And here is group 13. Now, boron, first element in group 13, has n equals 1, n equals 2 orbital. So again, the n equals 2 orbital is the valence orbital, and that's true for any period 2 elements. Talked about that. And we see that boron, the first element in group 13, has 3 valence electrons. Go down one period, we have aluminum, still group 13, has added an extra orbital, but yet still has 3 valence electrons. So far the pattern is group 1, 1 valence electron, group 2, 2 valence electrons, and group 13 has 3 valence electrons. So that pattern will continue. Group 14 has 1, 2, 3, 4 valence electrons. Group 15 has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 valence electrons. Group 16 has 6 valence electrons. Group 17 has 7 valence electrons. And you may predict that group 18 has 8 valence electrons, and you would be correct for all elements except helium, which is the exception. So helium only needs to fill that n equals 1 orbital. So helium will have 2 valence electrons, but every other group 18 element will have 8. So let's go back to our annotated periodic table and actually annotate that. So what we're going to do here is we are going to record on the periodic table itself the number of valence electrons down each main group element. So we're going to start with group 1, and group 1 will have 1 valence electron, VE. Group 2 will have 2 valence electrons. Remember, we're skipping the transition metals. We'll talk about those in just a minute. Group 13 will have 3 valence electrons. Group 14 will have 4 valence electrons. Group 15 will have 5 valence electrons. Group 16, 6 valence electrons. Group 17, 7 valence electrons. And group 18 will have 8 valence electrons, all except helium, which has 2 valence electrons. So now that we know the pattern around main group elements, we can go ahead and see how valence electron number predicts what the charge of that element will be when it becomes an ion. So the first thing we have to remember is our periodic trends. So recall that as we go left to right across the periodic table, we tend to go from metal to non-metal. We can see that here because metals are pink, non-metals are blue. So left to right across the periodic table, we tend to go from metals to non-metals. We know that left to right across the periodic table, ionization energy increases. And ionization energy is the energy needed to remove one of these atoms' electrons. So left to right across the periodic table, ionization energy increases, which means it's harder and harder to take away these electrons from the elements as you go from left to right across the periodic table. The other periodic trend here is as you go left to right across the periodic table, electronegativity increases, which means that these elements become better and better thieves of electrons as you go left to right across the periodic table. So to summarize that, we could say that lithium, a metal at the far left of the periodic table, will have lower ionization energy and electronegativity relative to fluorine, which is on this side, the right side of the periodic table. So lithium will be very bad at holding on to its own electrons and very bad at stealing others' electrons, where fluorine will be very good at holding on to its own electrons and be very good at stealing electrons. So lithium will lose electrons, fluorine will gain electrons. We know this because lithium is a metal, fluorine is a non-metal, and those are the patterns that we've come to expect from these types of elements. We know that because lithium is going to lose its electrons, we are going to lose 1 valence electron. And if we lose 1 electron, then we create an ion. And because we're losing a negative charge, that ion will be positive. And since we're losing 1, it will be a positive 1 charge. Now, beryllium, also a metal, is going to lose its valence electrons. So since it's losing, it's going to be positive. And since it has 2 valence electrons to lose, it'll be a positive 2. Now, we have also seen charges be written as 1 minus or plus, 2 minus or plus, 3 minus or plus. That tends to be the correct way to write oxidation numbers, which is what we're doing here. So you can write +1 or you can write 1 plus, either way, as long as you know what the charges are and why those charges are forming, I'm happy. So let's skip the transition metals, talk about those in just a minute, and jump to group 13. Now here's where it gets a little bit more complicated because group 13 is mostly metals, but then we have boron, which is a metalloid. So in general, we will see that group 13, largely being composed of metals, will form a positive ion because they will lose electrons. And because they have 3 to lose, typically group 13 elements will form a ionic charge of +3. We're going to skip over group 14 for a minute. It's very complicated here. We have carbon, which is a non-metal. We have silicon and germanium, which are metalloids, and then tin and lead. So we're going to skip over group 14. Now let's think about our nonmetals, which really kind of take hold in group 15. We know nonmetals are really good at stealing electrons. So we know nitrogen and phosphorus are very likely going to steal electrons from metals. But how many are they going to steal? The pattern we've seen so far is that if I have 1 valence electron in a metal, I will lose it and form a +1 ion. If I have 2 valence electrons, I will lose both of them. -2 negative charges gives me a +2 charge. If I have 3 valence electrons, I will lose all of them, giving me a +3 charge. But what happens when I start gaining electrons? Well, first of all, I know that if nitrogen and phosphorus, group 15, gain electrons, it will be negative. But how many are they going to gain or lose? Well, that's where the octet rule comes into play. So the octet rule says that all elements, and I'm just going to go ahead and put a little asterisk there, want 8 valence electrons. So if all elements, we'll talk about that asterisk in a moment, want 8 valence electrons, then nitrogen is going to need 3 more. So if nitrogen gains 3 more electrons, so 5 plus the 3 it gains gives me 8 electrons, then it will form a -3 charge. Oxygen, sulfur, selenium have 6 valence electrons, but according to the octet rule, they're going to want 8, so they'll need to gain 2 more. So if I gain, I'll become negative. If I gain 2 more, I'll be -2. And then our halogens here, group 17, currently have 7 valence electrons. Again, they want 8, so they'll need to gain 1 more. Gaining will give me a negative charge. Gaining 1 will give me a charge of -1. Now the noble gases, my group 18s, they don't need to gain anything because they already have a full outer shell. So here's one of our exceptions here, right? Helium does not want 6 more electrons. Helium is happy because it has filled that outermost shell, which is the N=1 shell. So my noble gases will form 0 ionic charge because they're happy as is. So now we know the charges of the main group elements, all but group 14. Now group 14 is a little complicated because we have nonmetals, metalloids, and then these metals are special as well. So I typically just put a question mark here because who knows what the heck these guys are going to do. We'll talk about those when we need to. So the last thing I want to do here is talk a little bit more about some of our transition metals, which remember start at group 3 and go all the way to group 12. So anything from group 3 to 12 will be our transition metals. So let's talk about these. The word transition means to change, right? So the reason these things are called transition metals is because they can change their valence electron number, which means we can't just assume that they'll have X amount of valence electrons with an X positive charge. We have to know a little bit more about them. So we are going to focus on a few specific transition metals. We're going to look at iron, nickel, copper. We're going to look at zinc, cadmium, and silver. And we are also going to look at tin and lead. So again, we have the transition metals that we're going to focus on today, which are iron, nickel, copper, zinc, cadmium, and silver. And then we're also going to look at group 14 elements, with these weird ones, tin and lead. Now, the transition metals that we're focusing on are just the ones that come up the most in our introductory course. But all of these transition metals will have special rules about their electrons. So the first thing that we want to take a look at here is iron. Now, I said that a transition metal can have multiple different valence electron configurations. Iron can have either a 2 valence electron configuration or a 3 valence electron configuration. So iron can have 2 VE or 3 VE. This will end up giving me an iron that could have a charge of +2 or +3. The next one I want to talk about is nickel. Nickel, again, can have 2 valence electron configuration or 3 valence electron configuration. So my nickel can have a +2 charge or a +3 charge. Copper can have 1 valence electron configuration or 2 valence electron configuration. So copper can be a +1 or +2 valence electron, ionic charge. So these are the transition metals that we see the most commonly in our course with multiple charges, and those are the most common charges. But I have a few more starred here. Now, zinc, cadmium, and silver, even though they are transition metals, can actually only have one valence electron configuration. So zinc can only have 2 valence electrons. So it's kind of a transition metal that can't change. It'll always have a charge of +2. The same is true for cadmium. Cadmium can only have a 2 valence electron configuration. So cadmium will always be a +2 ion. And then silver can only ever have a 1 valence electron configuration. So silver would always form a +1 ion. Now these are all positive because they're all metals. They'll all lose their electrons. So if you take an advanced chemistry course, you'll find, of course, that all of these transition metals have different charges, different valence electron configurations. You'll also find that there are more than what we've listed here. But for the introductory course that we are involved in, we're going to keep it simple. So then I have tin and lead, who are not in my transition group, but actually are transition metals. So they're a little weird. This group 14 is a little crazy. So tin can have a 2 valence electron configuration or a 4 valence electron configuration, which means tin can have a +2 ionic charge or a +4 ionic charge. And lead is the same. Lead can have a 2 valence electron configuration or a 4 valence electron configuration. So lead can have a +2 or a +4 charge. Now, this is what we have today annotated on our periodic table. So we have all of our main group element valence electron numbers and charges. We know that metals having low ionization energy and low electronegativity will lose electrons, becoming positive charges. We know that nonmetals with high electronegativities and high ionization energies will gain electrons, becoming negative ions. We know that our noble gases will neither gain nor lose because they have full octets and they're happy. And we know that some of the more common transition metals have these charges. A few transition metals don't change, and then some non-transition metals can change.